Hi, and welcome to this walkthrough of the Sweatshirt Incorporated mini case. So we are going to formulate it as a linear programming problem, and then you can watch the video where it is solved in Excel afterwards. So we're going to go through the 4 steps, defining parameters, variables, objective function, and constraints, and then we'll summarize it all in a big linear programming model. Or actually this one is not that big, but anyway. To start out with, we will look at step 1, the parameters for this model. The first thing we are told in the model is that, or in the case is that we have 3 different periods we are looking at. We are looking at autumn, winter, and spring. And in each of these 3 periods, we have some costs. So there's a cost per hour. And that depends on the period. So we have in autumn, we have in winter, and we have spring period. And in the autumn we pay $4.5, in the winter we pay $6, and in the spring we pay $5.50 per hour. In addition, we have hours used per sweatshirt. So per sweatshirt, and that is 1.5 hours. In addition, we have some inventory cost per quarter. So there's a cost incurred every quarter we have a shirt on or in inventory. So that's an inventory cost per shirt per period, and that is $0.9. And then we have some forecasted sales. And that also depend on which period we are in. So in autumn, there will be a forecasted sale of 125 shirts. In the winter, there's forecasted 350. And in the spring, we expect to sell 75 shirts. Okay. So that's basically all the parameters we need in this model. So let's put that up there and then continue with step 2. And that is the variables. Okay. So we are gonna figure out how many shirts we should produce in each period, but also we are gonna use variables that keep track on how much we have on inventory in each period. So this is an example of in the first lecture I told you that you could look for a definition. When you look for a definition of variables, you could look for what impact or what decision has an impact on the objective function. So in this case we have some inventory costs, so that is of course related to how much we have in stock. So we are gonna define variables PA, that's the production of shirts in period autumn, like that. Likewise, we have PW, that would be the production of shirts in winter. And we have PS, that'll be in spring. But then in addition to that, we'll also have a variable LA, which is the inventory level ultimo, that is in the end. In ultimo autumn, we have LW, that's just in the end of the winter. And then we have LS, that's the inventory in the end of spring. Okay, so that's the variables we are gonna use in this model. Then we need to go to step 3. And that is the objective function, abbreviated like that. So we are gonna minimize the total cost incurred here. Okay, so this means that we will be minimizing the production cost plus inventory cost. So that was an oral description of that. Now we need a mathematical. So we know that we use 1.5 hours each time we produce a shirt, and then we have some per hour costs. So if we sum here, we start by writing, that wasn't very pretty. Start by minimizing. So then we know that we use 1.5 hours on a shirt, no matter what period it is produced in. And then we know that producing a shirt in the autumn cost us $4.5. So we say 4.5 times the production in the autumn, and then finally we multiply by the number of hours we need to use here. In the winter it cost us $6, so we say $6 times how many shirts we produce, and then to that we add the $5.5 it costs to produce in the spring, like that. And that will be the production cost. To that we have to add the inventory cost. And the inventory cost, that is just 0.9 times how many items we have in stock. So that's 0.9 times LA LW plus LS. So the amount we have on stock at the end of the autumn, the end of the winter, and the end of the spring times the inventory costs. So that's the objective function. We want to minimize the total cost of production plus the cost of having items on in the inventory. Okay, then we can continue to step 4, which is the constraints we need to define now. And here we have a very classical inventory model where we need a constraint of the following form. We need starting inventory plus the production minus what we sell, so that's the demand, has to be equal to the ending inventory. So think of it as we start with something in the inventory and then we produce something. So that's the total amount of stuff we can sell in this period. Then we sell something, that's the demand, and what we haven't sold yet, so the starting inventory plus production minus what we sold, that should stay in the inventory. So we can make what is that called? Constraints that describe exactly this. In our case, it is quite nice to rearrange it a bit. So we have that starting inventory plus the production minus ending inventory equals the demand. And that is simply because we like to have the numbers, the constants, the parameters, we like to have that on the right hand side here. And in this case, we know the forecasted demand. Okay, so let's formulate these constraints. We need one of these constraints for each period. So starting with the autumn, we know that the starting inventory is 0. Then we have some production in this period. That's PA. And then finally we have the ending inventory. That's the variable LA. And that has to equal the forecasted demand, which was 125. Like that. Okay, then we have the winter. The starting inventory of the winter is the ending inventory in the previous period. So this means that the starting inventory here, that's the ultimo inventory level in the autumn. So that's the starting inventory plus the production in the winter minus the ending inventory in the winter. That has to equal the forecasted demand of 350. Of course, we also need one in the spring, like that. The starting inventory of the spring is equal to the ending inventory in the winter. Then we produce, and then we put something in stock. So that's the LS, and that has to equal 75. And then we need the non-negativity, which basically just says that LA, LW, LS, PA, PW, PS should all be greater or equal 0. Okay, we could have been a little more economic about the definition of the variables here. So we could have said instead that, okay, PJ is equal to the production of shirts in period J, where J can be in either autumn, spring, maybe we shouldn't forget the winter, and then spring. and we could say Lj is equal to inventory ultimo period J autumn, winter, and spring. This gives us a little more condensed formulation of this. Okay, because then we could have written this last non-negativity constraint as Lj, Pj should be greater or equal 0. Then we use the logical quantifier for all j in autumn, winter, and spring. Like that. So that was just a side note. Now we need to write up the full mathematical program. That could be right here. So we are going to minimize 1.5, that's the number of hours, times 4.5 PA plus 6 PW and 5.5 times PS plus 0.9, that was the inventory cost, LA, LW plus LS. Then we need the constraints for each period. We needed a 0, point the production in A, minus the end in inventory. That should be equal to 125. Then we needed the starting inventory in the winter plus the production in the winter minus the ending inventory of the winter. That should be equal to 350. And for the last period in the spring, we need the ending inventory plus the production in the spring minus the ending inventory in the spring. That needs to be equal to 75. And Pj, Lj greater or equal 0 for all j in autumn, winter, spring. So that's the linear programming model for the sweatshirt case. One thing you could notice is that we don't have anything telling us what is going on after the spring period. So this means it might not make any sense to put anything in the inventory of the spring, given that we have a positive coefficient in front of the variable in the objective function. So we can already now, before solving this problem, say that we know that Ls will be equal to 0. So that is an observation we could use. Okay, now you should continue with the video showing how to solve this in Excel.